Continuing down the number line, I'd like to give you a little more information on rational and irrational numbers. Rational numbers include fractions, decimals, square roots that have a repeating pattern or that just plain end. For example, 12/4, that improper fraction, becomes 3. If we were to look on a number line itself, 3 is represented. It's clearly understandable. If we have a fraction like 15/2, that one reduces to 7 1/2, or you could say 7.5. That too is recognizable, easily recognizable on a number line. 7 1/2. Here we see it between the 7 and the 8. So we have a very clear understanding of where that falls on a number line. If we have a fraction like 1/3, that has a repeating pattern. It doesn't work out evenly. It keeps on going to infinity, but the pattern is clearly recognizable. And in fact, you could say this as 0.3 with a bar over it. That also means that the 3 is repeating. It goes on to infinity, however. Or you could have a pattern, a repeating pattern like this one. And in this case, we would just put a bar over the 1 and the 2 because that's the part that is repeating. We don't have to keep on going with that, but that shows you that it goes to infinity, and this is a shortcut for it with these bars over the repeating part. So you can see that the rational numbers make sense. They're clearly represented on a number line, or the pattern repeats enough that you can get a sense of the continuity. Irrational numbers, not so much. On the irrational side, the fraction, the top-heavy fraction 22/7, which is referred to as pi, this is used in calculations for circumference of a circle or area of a circle formulas. At any rate, 22/7 is sometimes used, sometimes the decimal equivalent of 3.14. They truncate it here just so it's workable, but the actual decimal keeps on and on forever in a non-repeating pattern. At least this one stopped. Or the 1/3 gave us 0.333. It was a repeating pattern that had some continuity to it. So at any rate, there's an example of the fraction turned decimal. If we were to do the square root, a perfect square in the rational side, perhaps the square root of 36, would branch definitely into a 6 times 6. We can use one of the 6's to represent the pair, so the square root of 36 is 6. That's nice and clean. Again, you can see that on a ruler, on a number line. But if we had the square root perhaps of 2, this one can't branch into a doubled number. We can't get factors of 2 other than 2 times 1, and those certainly don't match. The square root of 2, on the other hand, gives us this really hard to wrap your head around decimal. That is, again, a non-repeating. It just goes and goes and goes forever. So rational, these make sense. Irrational, it's just hard to imagine. Another symbol that's used, this is another Greek letter, phi, and that one has a decimal equivalent of 1.61803 3, 9, and it kind of spirals out there into space too with its non-repeating pattern. This particular symbol is connected with something called the golden ratio. You have to understand that I'm trying to give you an overview of what is included in these categories. But even something like this golden ratio, it's hard to think that you could understand something like this, but it is a fascinating topic. And hopefully I will perk your interest to look into these further. This golden ratio creates lovely patterns, especially in nature, and a lot of mathematics is really used to unlock the secrets of nature anyway. So it's really just a fascinating topic all the way around. But this is just a slight overview. I want to give you an understanding of the number system itself and basically what jumps into these different categories. So treat yourself to look that one up if you are so inclined.